Good evening, everyone. I trust that you're all doing very well. Welcome to the third episode of Scientifically Speaking Season 6, an engaging online lecture series where we bring world renowned scientists straight to you, the curious minds of high school students and teachers. Over the past 5 seasons, we have covered a vast variety of the most fascinating topics in science. Everything from the mysteries of data science to the wonders of astronomy, the origins of life, the secrets behind the science of food, animal behavior, and even infectious diseases. And now, we're thrilled for you to be a part of season 6, which is going to be even bigger and better. I am Kangna, your host for today's exciting session. I have a background in biology and completed my MSc at Ashoka University, and now I'm thrilled to be working with the Research and Development Office at Ashoka. I look forward to guiding us through an informative and gripping session today. So, without further ado, let me introduce our speaker for today. Please join me in welcoming Dr. Sushmita Saha, Assistant Professor of Physics at Ashoka University. An experimental physicist, Professor Saha heads the Complex Magnetic Characterization Lab at Ashoka, specializing in the magnetization dynamics of thin films and nanostructures. Her lab employs various techniques to explore magnetic fractals, skyrmions, ferrimagnetic thin films, and ultra-fast magnetization dynamics. Professor Saha has earned her PhD from SN Bose National Center for Basic Science, India in 2016. After that, she moved to ETH Zurich, Switzerland to pursue her first postdoctoral research. In 2020, she joined Uppsala University, Sweden, to pursue her second postdoctoral research work, and subsequently, she joined Ashoka University as a faculty in the Department of Physics. Today, Professor Saha will discuss the fundamental principles of magnetism, exploring how magnets generate magnetic fields and their applications in everyday technology, from motors and data storage to medical imaging and advanced scientific research. So let's get started. Please feel free to drop in any questions you might have in the Q&A box on your Zoom screen, and we'll address them at the end. A very big warm welcome to you, Professor Sushmita. We eagerly anticipate your session and can't wait to learn something new today.
Uh, Thank you, Kanda. Thank you for this nice introduction. And welcome, everyone. So today I will be talking about magnets. Let's start a journey in the world of magnets. So in your day-to-day life, knowingly, unknowingly, you use magnets almost all the time. So the thing is, the magnet that today I will be talking, so I will share my screen. So today I will be talking about magnificent magnets, and I will take you from the compass needle time to a high-tech gadget. So in everywhere you use the magnet in your day-to-day life. So the first thing when I talk about magnet, it comes the fridge magnet that we can regularly see, right? So magnet is a material which produces a magnetic field. So there I have given some example of the fridge magnet. And in case of magnet, they have iron, cobalt, and nickel. They are mainly the magnetic materials. Here I have shown you two examples. One is an horseshoe magnet and another one is a bar magnet. So here I gave you the example of normal permanent magnet. Now in this case, here in this photo, what I have done, I put some iron dust into it, and you can see most of the iron dust are attracts at the edges of this magnet. So this is how the magnetic field created by this magnet looks like, magnetic field line of this magnet. Another example is our Earth. Earth is a magnet. So here we have the Earth, and this Earth has a magnet there. And also, the sun also has a magnetic field. And when these two magnetic field interacts, you can see auroras, which is very fascinating thing. So in nature also, the magnetic field you can see. So the discovery of magnets are actually, it's like very old. The day people first invented iron, that day the discovery of magnets started. So what they discovered first, they discovered lodestone, that is natural magnetite, which can attract iron. Here I have given a photo. And then there was a book written by William Gilbert. It's about on the magnet and the magnetic bodies and on the great magnet the earth. In this book, he first described that earth is a magnet and earth is made of iron, and it is important to consider that earth also creates a magnetic field, and it also has a north pole and a south pole. So say I give you a magnet and now I ask you to break the magnet. What will happen? So in case of a magnet, you have two poles. One is north pole, another one is south pole. If you break it, what you create? You create another magnet which again has a north pole and south pole. And if you consecutively breaking it, then again you will get another smaller magnet with north pole and south pole. So if I give you a magnetic material, you have small north poles, south poles like that. The moment you put another magnet close to it, the north poles will be attracted to the south pole and they will align in the direction, and then it will also induce the magnetization. That is the reason when the lodestone and I have some iron, it attracts the irons, that lodestone attracts the irons there. So, but this is an origin that I am talking about macroscopically, right? I'm talking about a bar magnet and I'm breaking it into smaller pieces. But scientifically, it is not the case. Scientifically, what is there? If I break the mini material to smaller dimension, what I get? I get an atom. In case of atom, you have a nucleus and then the electrons orbiting along this, around this nucleus, right? So if I give you an electron has either upspin or downspin. So electrons can also behave like a magnet, and it creates a magnetic field because electrons are always moving along this orbital. Now, there are few materials, you know, or we know that to achieve a ground state, what we need paired electron. So in every state, it can be one up electron and one down electron present. So I gave you four examples, four different types of material: copper, nickel, copper, nickel, cobalt, and iron. If you see carefully, all of them has 3D orbitals, and in 3D orbitals for copper, all of the 3D orbitals are filled, one up, one down, right? That means I have a electron with upspin and downspin. But in case of nickel, cobalt, and iron, you see in 3D orbitals, they are not paired. They have only one type of electron present, either up or down. So what is happening in case of copper? When up and down electrons are present, they are paired, the total electric field cancel out and there is no net magnetic field produced. But in case of iron, cobalt, nickel, as they have unpaired electron, that means overall there is a magnetic field created, and that magnetic field is present into this system. That is the reason the example I gave in the very first slide, that magnetic materials are mostly iron, cobalt, and nickel. So let's talk about, till now we were talking about solid bar magnets, like which has the property and it gives you the magnetization at a moment. But now we can also create the magnetic field. How can we create it? Say I have a current carrying wire. If I send current through it, then Faraday's law of induction plays an important role and magnetic field is generated. Like here, the moment I create a current flowing through this wire and magnetic field is generated. And this magnetic field attracts these pins and these pins are placed there. So we can create this magnet. These are called electromagnet. Similarly, what we can do, we can, here, moving current can give us magnetic field. Similarly, moving magnet can also give us current. So here, you see the magnet is moving, and the moment magnet starts to go through this coil, you see here the current is appearing. So moving magnet can also induce the current and we can create the electromagnet. So in our day-to-day life, we always use electric motors, like in our fan, in refrigerator, in air condition, we have these motors. And how it works? In case of electric motor, what you have such current carrying loop and it placed in between a magnetic field. Now, when you rotate it, when you send current through it, a torque is acted into the system and this loop start to rotate. And this was first discovered by Scottish monk Andrew Gordon, and it was experimentally proven in 1740s by Benjamin Franklin. So there I have given some more examples of the magnet that we use. In case of windmill, we use this permanent magnet. But in case of household appliances, we always use the electric motor and the magnet there as well. So now talk about very interesting thing. This is called eddy current. So in our we use induction cooktops nowadays, right? How induction cooktop works? In case of induction cooktop, what do you have? You have a copper coil and you send current through it. The moment current going through it, according to Faraday's law, magnetic field is induced. And this magnetic field, when we placed a pan on top of it, it's a metallic pan, and it creates some current carrying small loop into that pan. And as a result, it heated up, and this heating helps you to cook the food. And this current that is created into that conducting materials, it known as eddy currents. And eddy currents creates a magnetic field that opposes the change of the magnetic field as well, right? And that eddy current is here used in the induction cooktop. Here I have shown a zip file. Here current is flowing and I have a conductive material and magnetic field is created, and this magnetic field induced a current into this conducting material, and this is called eddy current. Let's talk about superconductors. So the superconductors are, in general, we have metals and metals are conducting, because if we send current through it, what happened? It can flow the current easily. Okay, like copper, if you consider copper, which has a low resistance and it can carry the current. But there are few materials which shows no resistance after a certain critical temperature. These materials are known as superconductors. So in case of superconductors, you can see there is a critical temperature and above which the resistance is increases, but below this critical temperature, resistance is just 0. That means it can carry the current without any resistance from it, without any. So in this case, what happened that the current is flowing without any opposite force or applying to that. So these are the examples: yttrium, barium, copper oxide, YbCO, and niobium titanium is the examples for the superconductor. This superconductor shows a very interesting effect. This is called Meissner effect. What is Meissner effect? In case of Meissner effect, what happened? Above this critical temperature, magnetic field flows through this material. But if I go to below critical temperature, it starts to deflect the magnetic field. Here you can see I gave an example of it. This is a superconductor and I put a magnet here, and you see this magnet is levitated by this superconductor. This is called superconducting levitation, and that is used in our maglev train. And in maglev train, what do you have? You have this superconducting magnet, and then you have the train going on. And when it going on, due to at below this temperature, as it repel it, then it is not touching the path, but it is moving and it is going faster. So maglev is a method which an object suspended into no support than the magnetic field. So it is only supported by the magnetic field. And in this case, what kind of magnet we use? We use superconducting magnet. So this is a superconducting magnet. This is a coil and superconductor is flowing through it. So, and this when superconductor flows through it, the magnetic field that is created, it is around 15 Tesla. So just to give you an example, how much that amount is, if I consider the Earth's magnetic fields on the surface of the Earth, it's around half a Gauss. And 10,000 Gauss is in 1 Tesla. So you can imagine how strong that magnetic field is when I am talking about superconducting magnet. But why am I talking about this? We use this superconducting magnet in our day-to-day cases, especially in our MRI instrument. How MRI works? MRI is magnetic resonance imaging. So our body is full of water molecules, right? That is, hydrogen is present. Now, what we do, our body, we placed it in between two superconducting magnet, this strong magnet. And what happened? And all these hydrogen atoms, they behave like a small magnet and they aligned in north and south pole like that. So when it is placed in presence of a magnetic field, all these magnets are aligned in that particular direction. Now what we do, we applied a very strong RF field into that system. The moment RF field is applied to that, this orientation disrupted. As a result, they become very unorganized. Now, then this RF field applied and we take it out, we switch it off. But when we switch it off, this magnetic field, due to presence of this magnet, they try to align along the direction of that applied magnetic field. And at that time, it resonates and it emits certain kind of image. It emits some frequency, and that is used for imaging the different parts of the body. So it can use to image the organs, bones, muscles, and blood vessels. So we also use magnet in doing biology or in medicine as well. So now, as I am talking about magnet, there are different types of magnets. So there are mainly 4 types of magnet. First are ferromagnet. In case of ferromagnet, the spins are always aligned parallel to each other. Like here, if I give you a ferromagnet, you can see all spins are aligned in this direction. Now we have antiferromagnet. In case of antiferromagnets, spins are arranged antiparallelly. Then there is the ferrimagnet. In case of ferrimagnet, what is there? The spins are, you can see here, the spins are aligned antiparallel with each other. But if you see, the magnitude is different. That means this one has large magnitude, this one has small magnitude. So overall, there is an up direction magnetization presence. And then there is a paramagnetic material. And in case of paramagnetic material, the spins are randomly oriented. So say I want to give you an example of the ferromagnets. So iron, cobalt, nickel, they are ferromagnets because they have the spins aligned in the particular direction. In the example for antiferromagnets are nickel oxide, iron oxide, manganese oxide. The ferrimagnets examples are the magnetites, yttrium, iron, garnet, and the paramagnets are aluminium, platinum, and the oxygen. So in this case, these are the types of magnetic materials present. So I told you that here the spins are aligned parallel and anti-parallel to it. But what does that mean? That means that if I give you a magnetic material and if you make it smaller structure to it, what you can see, so this is a very small part of a magnet. At H is equal to 0, when there is no field applied, you can see they have different part, and different part the spins are aligned in a particular direction. But overall, you can see it is randomly oriented, but different patches have a particular orientation. These are called magnetic domains. Now, when I applied a magnetic field here, as I shown, all the spins try to orient along this direction of the magnetic field. And then the whole system achieve a saturation magnetization. And here I give you a quick example how these domains are look like. So this is a cobalt platinum thin film which has a thickness of around 90 nanometer. And here, this white and black part, they are different kind of domains. White means the spins are aligned in up direction, let's consider. And in case of black, the spins are aligned in the down direction, right? So this is a image of a magnetic domain. And if you see the dimension of this is in micrometer range. Now, when I apply the magnetic field to this system, you see here, most of the parts are looks flat. There is no such structure present. That means most of the part, the system is saturated. All my different domains are aligned along the direction of the magnetic field. That is my magnetic field I applied, minus 29 millitesla. But if you carefully note this small part, can you see there are some white dot present? What are those white dots? Those white dots are called magnetic skyrmions. They are topologically protected magnetic structures. Here I give you a schematic of these skyrmions that is observed in such magnetic thin films. So there it is very interesting because here the size can go to below 100 nanometer. When the size goes below 100 nanometer, these skyrmions can be used for various applications. What kind of applications it can be used? So there it is a magnetic skyrmion. In this case, you can see the skyrmions have this kind of structure, spin texture, and they are topologically protected. That means I can't destroy them by applying any other thing. I need to, like, it is topologically protected, so it can only be destroyed by applying a high magnetic field or something like that. So in this case, these magnetic skyrmions could be used for data storage. How I can say it can be used for data storage? Let's say here I have different, these are skyrmion, there is no skyrmion, then there is another skyrmion and no skyrmion. Now, when there is a skyrmion present, I call it 1. That means it is storing some information. No skyrmions means it is not storing any information, so it is 0. The fine thing about this is the skyrmions these skyrmions, if I apply certain current through it, they can move. That means I can store the data and I can also move them. Like here, I thought it should be working. Yeah. So here you can see I have shown I applied a current and the skyrmion is moving and this skyrmion is now rotating. So I applied a low current density here. And here I applied a current and in presence of DMI and then it destroys and this skyrmion is present. So that means the good thing is the skyrmions sizes are small and also we can control their movement by the application of electric current. Now the to create the skyrmion, we need a particular kind of interaction that is called Zylosensky-Moria interaction. And it is an antisymmetric exchange interaction, which is given by this relation. So recently, what we have done, we have studied the skyrmion-based universal logic gates and computational operation. So in our computer, we always use logic gate, right? So there it is a schematic of a NAND gate and it is a schematic of a NOR gate. NAND means it is not performing the AND operation and NOR is not OR, okay? So here, if you see the truth table for that, what is there? If I apply nothing there, my output will be 1. And when I apply something here, my output will be 0. So here, I have shown how these skyrmions can work as a as a logic gate, universal logic gate. You see, I have a skyrmion. I applied a current. This skyrmion moves and it goes to through the structure. And finally, what you get the skyrmion and it is present here. So here you have this criteria. You have nothing in this, but you have one skyrmion here, and your output is also giving you another skyrmion. So then we come to the NOR operation. In case of NOR operation, let's consider this. Again, I applied a skyrmion here. There is no skyrmion, but now you know in your output it will be 0. And let's see whether I am getting 0 or not. So this is the skyrmion moving through this wall, and then it is going. When it is coming here, you will see it collides and then it vanished. Yeah, say both the skyrmions vanished. So this way, what we can do, we can use the skyrmions and we can use them for logic operation. After logic operation, the things comes whether skyrmions can do the computational operation as well, like whether it can add 2 bits or it can add 3 bits. Yes, it can do that, and we have shown that it can work as a half adder and a full adder. So it can do the addition as well. So like here, I have 2 bits coming, and when it is here, you can get what will be the output for the addition of this 2 bit. You will be 1, and then here it will be 0. So you have a sum and you have a carry. In this case, your carry is 1 and your sum is 0. Okay. So till now, whatever we have discussed, we have seen that I have a bar magnet. If I go to lower dimension of that bar magnet, what I can see, I have these magnetic domains in 100 micrometer range. If I go further, then we can again see magnetic domains that is also present in 10 micrometer. Now, if I go to smaller dimension, 100 nanometer or 10 nanometer, we can also make magnetic nanoparticles, magnetic structures like this. So we can play with the length scale of the magnet. Similarly, we can also play with the time scale of the magnet. So I will be talking about how magnetic recording works. You will see that magnetic recording works in 1 nanosecond time scale. But additionally, we have various other interaction, like in picosecond time scale, we have magnetic demagnetization process. Then we also have optical manipulation of the magnet, which occurs in hundreds of femtosecond time scale. If I go further in time scale, then we can see the exchange interaction as well. So magnetic material and magnetization dynamics could be useful for a longer length scale and a longer time scale as well. So we can play the time scale from nanosecond to femtosecond, and we can also play with the dimension of the magnets from some micrometer to nanometer range. So, nowadays we use the data storage a lot, right? So there I found some images and I just saw it will be interesting to see how it evolved. These are the floppy disks that we used in 1980s and sometimes. And then we have the CDs, we have DVDs, we have the USB stick, SD cards, and now everything is in cloud, right? And also, if you remember, like we use nowadays magnetic hard disk, which can store 2 TB data. And how it works, it's mainly based on magnetic materials. So why we are going for magnetic devices with compared to the semiconducting devices? Because our technology presently is based on semiconductor. But today I want to propose that we need to head to a technology which is based on magnetic materials. But why am I going to do that? The main advantages for magnetic devices are they have smooth surface and interfaces. In case of semiconductor, the depletion layer is micrometer to nanometer length scale. The spin diffusion length in a magnetic devices are in nanometer range, whereas in semiconducting devices, they are in micrometer range. So magnetic devices is also low resistivity and we can vary. In case of semiconductor, also we can do the variable resistivity. Spin polarization is present in magnetic devices as well and also in semiconducting devices. Another interesting thing is magnetic materials are anisotropic, whereas semiconductors are isotropic. Why it is important? That means when they are anisotropic, I can use some particular direction of the magnetization of these materials for certain application. I will come to that in few slides, in next slide probably. So this is a magnetic material. Initially there, my magnetic material is randomly oriented and it is giving you a random orientation. Now I applied the magnetic field. So initially what is happening? This magnetic materials or random orientation, all the domains are trying to align along the direction of the magnetic field. And here you see all the domains are aligned along the direction of the magnetic field that is applied in this side. Now, when I switch them, they did not follow the old path from where it comes, but it takes another route, that is this path. And when it goes there, here you see my field applied is 0. Sorry, my field applied is 0, but my magnetization is not 0. It has some certain magnetization present. So if I want to make my magnetization 0, what I have to do? I have to apply some certain magnetic field in the negative direction. That I did. And here again, I get my magnetization 0. That means my spins are again randomly oriented. Now, if I further increase the magnetic field in the negative direction, then all my domains will be aligned along the direction of the negative magnetic field direction, right? So this loop is called the hysteresis loop of a magnetic material. And that is the point where we can use the magnetic material to store the information. So here I have shown the hysteresis loop of a two different kinds of magnetic system. One is a 3 micrometer magnetic square. Another one is 100 nanometer magnetic square. You see, in case of 3 micrometer square, the loop is pretty broad, right? Whereas for 100 nanometer square, the loop is pretty thin. So in case of this pretty broad structure, sorry, in case of 100 nanometer, it is pretty broad. And in case of 3 micrometers, it's pretty thin. So my 3 micrometer system is behaving like a soft magnet, whereas my 100 nanometer, when I reduce the size, it is behaving like a hard magnet. What does that mean? That means I can make my spin oriented in this upspin direction, and I can let it stay for longer scale. And then when I switch the field, all the upspin will be going to the downspin. And say my upspin is considered as state 1. Then when it switches the spin, it will be state 0. And then the information will be stored in state 1 and in state 0. Like here I have shown. So here, this orientation store a data with a state 1, and this orientation store a data with state 0. Now, so in a magnetic material, they are non-volatile, they are non-destructive, and we can use it to store the data. But how am I going to read this data? So this is our today's magnetic hard disk. In today's magnetic hard disk, what we have the magnetic material, and depending upon their orientation, we can store the data, and this read and write head is discovered. This read and write head is based on giant magnetoresistance. This is called the GMR effect. And for that, Peter Grunberg and Albert Fark received the Nobel Prize as well. What it do? It gives you the various resistance depending upon the orientation of the magnetic field. Say I have a 3 layer of magnetic material. if the spins are antiparallelly arranged, then the resistivity is very high. But when they are parallelly arranged, the resistivity is very low. So you can consider that depending upon this resistivity, for very high resistivity, no current will be flowing, whereas for low resistivity, current will be flowing, and then you can store the data and you can read and write the data using this magnetic read and write head, which is based on the GMR effect. So this is a photograph of the first MRAM product, that is in 2006 it was taken, and now we are using this magnetic random access memory in our day-to-day hard disk as well. So till now, whatever I am talking about current flowing through a system. So when current flows through a system, that means I have a charge flowing through it, right? When charge flows, what happens? The charge means electrons are flowing, they scatter, and then they create heat. This is called Joule heating. So this Joule heating, what makes, you can, if you can check it by yourself, your computer becomes hot, right? And this is because of this Joule heating. So if we want low power devices, we need to control this Joule heating. That brings me to the advanced part of the talk, which is spin wave. What is spin wave? Say I have a magnetic material, ferromagnetic material. In ferromagnetic material, I know all my spins are parallelly arranged. Now I part up the system. When I part up the system, this perturbation propagates in the form of a wave. But if you consider carefully, there is no charge current involved to it. That means the propagation of this wave is due to the spins present into the system, or we called it magnons present into the system. So it is a Joule heating free system. So it can give me low power devices. Like here, so the goal of spintronics is you excite a spin wave, then your spin wave is propagating and carrying the information with you, and that spin wave will be used for transporting information. And as it is related to magnetic material, we can also do miniaturization. That means we can go to smaller length scale for that. So for that kind of magnetic devices.
Professor, sorry to interrupt. We're nearing the end time, so I was
Yeah,
kindly.
so this is my last slide.
Yeah, sure.
Okay. So based on these spin waves, we have proposed various kind of advanced technologies. Like we have proposed magnetic racetrack memories, we have proposed spin transistor and other devices as well. So in conclusion, I can say that we use magnet in our day-to-day life. It is used in MRI machines, in simple refrigerators, in fridge magnet and everywhere. But it also has a potential to be used for high-tech gadgets as well. Like one of the demonstration is already done, but others could be done as well. Like the spin wave based devices, Fermion based devices, those brings a new field of research called spintronics and magnonics. And my research is on that. And I would like to motivate the students, the young minds, to give more thought about this field and contribute in this field significantly. And thank you. I will be happy to answer the questions. Thanks.
Yeah. Thank you so much, Professor, for that insightful presentation. We really appreciate the valuable knowledge that you've shared with us today. And we will now begin with the Q&A round. So starting with our first question for today is, how has the understanding of magnetism evolved over time, and who were some key figures in its study?
Is it in the chat? Can I see the question? Yeah, could you please tell me again the question?
Yeah. How has the understanding of magnetism evolved over time, and some key scientists or some key figures in this
So the
field?
magnet, as I told, the discovery of magnets started long time ago from the Iron Age, right? But the main study started to appear in the field of spin, like magnets are used, but the moment we have the electromagnet, there it started. Then we have back electric motors. Then we have other devices like motors we use in day-to-day life, right? So that is the thing, that is the few parts that we are doing. And recently in spintronics, the GMR discovery gives you the main basis for the giant spaces for the magnetic materials for and their application in future spintronic devices as well.
Thank you. The next question somebody has asked, why do magnets attract and repel?
So magnet attracts and repels. Actually, it is the thing is, if you remember, I shared a slide. Okay, I think I need to go back. So if I give you a material, it has electrons evolving, right? When electron evolves, then it behave like a current carrying loop. And if you have a current carrying loop, then depending upon the direction, which direction current goes, it can show you which direction the magnetic field will be. So say you have two different kind of electrons with two different kind of spins. Then in one direction, it will be current magnetic field will be in one direction, and in another, it will be in the opposite direction. So that is the reason that magnet. So if they're in opposite direction, it will be different. And if they're in the same direction, then the total field will be addition of these two fields, right? So that is the reason when they add up, we call it is attractive. And when they cancel out, or then you can say they are repelling. So it comes from the basic of the electron, how the electrons are flowing to it.
Okay. Thank you. The next question is, every alkali metal group 1 also has one electron which is unpaired, so but they are not magnetic. Any reason for that?
Alkaline metal, okay. So if it is unpaired electron, it is not necessarily like they will always give you strong magnetic moment, right? It is coming from the unpaired electron part, but all unpaired electron is not always giving you they can be a paramagnetic material. That means if you apply a high magnetic field, only then their moment will be aligned in the direction of the magnetic field. But in case of ferromagnet, you have a spontaneous magnetization. That means if you take the material, in general, it has some magnetic information into it and gives you a spontaneous magnetization. So that is, I will say, it is the difference.
The next question is, how small can we go in size and still retain the magnetic properties? Like you were mentioning, if we keep breaking a magnet.
Yeah. So the thing is, in case of magnetic material, when I reduce the size, I have not shown that slide here, but you have different kind of energies that started to play a role. So you can consider that I am reducing my sizes only, but below a certain size, my system, like a single spin can also behave as a magnet, right? But if you want to do the application of it, then we have lithographically restrictions and sample fabrication restrictions are there as well. So I will say that then we have restricted, say below 50 nanometer, we can't grow magnetic nanostructures, right? But in general, if it is in general question, how small I can go, then I will say we can go smaller size also, it gives you the magnetic moment. Like electrons evolving, giving you a particular moment.
Somebody is now asking, why does current induce a magnetic field?
So current induces a magnetic field means when I have current means its charge is flowing, right? That means electrons are flowing. So the thing is, current carrying loop gives you a magnetic field. That means the moment I started with an electron evolving in a particular orbit. So if electron is flowing in an orbit, that means it is giving you a current. And when it is flows, it also creates a magnetic field perpendicular to the direction of its flow. So that is how that magnetic field is generated. And that is the reason when I send a current, it also gives you a magnetic field.
Okay, thank you so much. The next question is, you were discussing about eddy currents. So somebody is asking, are eddy currents also created when there is change in space or only with change in time?
So eddy current is created if I have so eddy current is created because I have current going through a system. So I have change in electric field, which is giving me the magnetic field. And this magnetic field is inducing some electric field again, or some current loop into my conductor. And then these eddy currents are created. So, okay. I am trying to go back to the slide where I have the eddy current. Yeah, here. So here you see my current is flowing through a wire. It is creating a magnetic field. And this magnetic field, and I have a conductive material there. This magnetic field is inducing current here. And then that is giving me the eddy current.
Thank you. Now someone's asking, do they emit photons when you say emit frequency? What they mean here is the hydrogen atoms in water when you were discussing the example of an MRI. So
Here.
yeah, it's basically they mean, do hydrogen atoms in water emit photons when you are saying that they're emitting frequency? Is that what that
No, it's not the proton. It is just the hydrogen atom. If you consider the hydrogen atom, it has a nucleus and electrons, right? When you placed it in a magnetic field, the positive goes in one direction and negative goes in the other direction. Then it behaves like a small bar magnet. Now, what you do, this bar magnet has a particular orientation, and if my field is applied in the vertical direction, then they are like that. Now, what I do, I put some RF frequency into it. When I put the RF frequency, my system disturbed, so they go random. Now, when they got random, and then I stopped my RF field, and now they are trying to come back to this older position due to this applied field direction, and that time they emits the radiation, and that radiation you use for the scanning of the images.
All right. The next question is, is the iron content in our blood attracted towards a magnet? What is magnetic therapy?
Iron content in our blood, say again, please, the question.
Yes, sure. Is the iron content in our blood attracted towards a magnet? And then the second part is, what is a magnetic therapy?
Iron content into the blood, no, it did not. It is mainly the water molecule which is affecting to this MRI. And magnetic therapy, I'm not very sure of it. So I don't know. I know the different kind of therapy like hypothermia, like that, but I'm not very sure about what is mean by magnetic therapy. I'm sorry about that.
Sure. We'll move on to the next question. In a rusty nail, FeO and Fe are both there. One is a ferromagnet and the other is anti. How would it behave?
So generally, if you see the rust, so it is a surface effect. If I give you a iron, and if it is placed in the environment for a long time, then it oxidized and it becomes FeO. And then it creates a coating on top of the iron, right? So you have an antiferromagnetic coating on top of a ferromagnetic material. So it's in the surface effect, but inside it will be the magnetic material. Is it that the question?
Yeah. Okay. The next question is, how is energy conserved when supermagnets levitate, allowing maglev to resist gravity?
Okay. So here, here I am using a very strong superconducting magnet, and I have a magnet. So in the train, you have the magnet placed, and you have a superconducting magnet, and then this magnet repels, because I told at below certain TC, it repels the magnetic field. That means my magnetic system will be, that my magnets will be uh, levitated, right? And now it moves, because this is changing, it's continuously changing, and then it also moved forward direction. So that is how it works. So that is the thing,
Okay, thank you. We'll move on to the next question. Can we use magnetism in satellites which might enable us to communicate and store data between Earth and space?
yes, I think so. I'm just not sure whether it is already used or not.
Mhm. Okay. The next question is, how ferromagnetic materials are slowly losing their magnetic abilities?
So slow ferromagnetic materials losing their magnetic ability, it could be due to temperature. It could be due to environment. Like I told, it can be oxidized, and then it can create another material coating on top of it. And it could be due to, if I drop it suddenly, and then it can disrupt its magnetic orientation, domain orientation, and it can lose its magnetization. So this can be definitely the ways it can lose its magnetic property with time.
Next question is, how can a small change in Earth's magnetism affect us? Why is it that Earth has a certain range of values for magnetic fields and not any other range? Also, would like to know if the Earth's field can disappear one day. It's
Okay.
a three-part question.
Yes. So the thing is, Earth has a magnetic field, because we have, okay, there should be an image somewhere. Yeah. So in our Earth, we have the very strong iron core inside, right? And that core is the main, origin, that it is giving me the magnetic field. And the if I know, and that this pole is also changing with time. It's changing very slowly, but it changes. And this field is very important, because from the sun there are different ions, and different ions that can give me a sun wind, and that is also another magnetic system. And this sun wind interfered with this magnetic field, and as a result, we get these auroras, different kind of. If there is a leakage of these ions in our environment, it interacts with the oxygen and other materials, and you can get these nice lights. So I will say that is how the Earth magnetic field is protecting us, and I don't think it can disappear suddenly.
Okay. Next question is, can magnetic fields have a particular manifestation and can those be quantum entangled? Are there applications in quantum computing?
Yes, it could be possible to use magnetic qubit. There are different kinds of proposals have been proposed. One of the proposal, I can say that I showed you magnetic skyrmions, right? In case of magnetic skyrmions, it is proposed that magnetic skyrmions can also be considered as quantum material, and it can be considered as quantum bit, because they are small, and their helicity could be considered as upspin and downspin as well. Not up and down, I will say state, up state and down state as well. So the helicity can be considered. So magnetic material has the potential to become a quantum material in future. Not only this, you can use any kind of magnet, like any material which can be show such kind of behavior. So it's possible.
We'll take a last question now. Is the quest for magnetic monopole still on? Are you hopeful? And why do we say that a magnetic monopole does not exist? These are two questions that I'm clubbing.
So magnetic monopole doesn't exist because I told you the moment I break a magnet, I always create a pair of magnets, North Pole and South Pole. I can't create a single North Pole. And in Maxwell's equation, we also have divergence of B is equal to 0. Divergence of B is equal to 0 means whatever going out, flux lines, that is coming back. So it can't be possible that number of lines going out is not equal to the number of lines coming in. It always has to be equal. Divergence of B is 0. But I just want to give you a very simple example. There is a system, it's called artificial spin ice. In case of artificial spin ice, there is a frustration present into the magnetic system. And due to this frustration, you can sometimes create a magnetic monopole, but that is locally created magnetic monopoles. But it is not exactly a magnetic monopole because you always have another magnetic monopole somewhere globally further away. So it is still a still an interesting problem to find out whether it is possible to find out magnetic monopoles or not, because it can't exist. But sometimes if you break some symmetry, you can initially create it, but it is locally created, and then this local creation of that monopole can go further, and there is another, if there is a plus magnetic charge, there will be another a negative minus magnetic charge in the Dirac string. So it is, yeah, it is a question. Yeah, and we are still looking for it. We are still trying to find out the answers for that.
There are a lot of questions, so we can take 2, 3 more. The next question is, what exactly is coercivity? Why is coercivity more important than retentivity for a permanent magnet?
Okay. So coercivity is here, the coercivity is when your magnetic system, so this is given by my coercivity. That width is given by my coercivity. And that means when I apply a certain magnetic field and then it becomes randomly oriented, that is giving you the coercivity of the system. And retentivity is when your magnetic field is 0, still you have some magnetization present into your system, and that is giving you the retentivity of the material. And the question is why coercivity is important?
Than retentivity for a
No,
permanent magnet.
for a permanent magnet, what do you want? If you want a permanent magnet, you want this loop gives you the energy loss as well. So if I give you a permanent magnet, that means you want its magnetization to stay for longer time. Otherwise, with time, as I discussed before, its magnetization will be loose. So you want this hysteresis loop to have a more area. And in this case, to get a more area, you need to have a large coercivity, but you also need a retentivity as well. If you are interested to storing your information, if you are interested to store the information, then you want upspin and the downspin. You don't want to go through different phases and change the system, right? You want to store your data either in up or in down. So in that case, retentivity is important. But for permanent magnet, as you want larger area, this hysteresis loop area should be larger. So you are more interested in coercivity.
Next question is, what are the latest innovations in magnetism research and how might they impact future technology?
So latest innovation, I told there is GMR, which is recently discovered, and it got the Nobel Prize in 2007. And as a result, we are using magnetic random access memory. So the read head and the write head used in hard disk are now based on this GMR. So this is the latest invention application wise. But without application, people are still working, like I am working on how I can use spin wave to transport the information, because that will give me low powered devices. Then Skyrmion based devices is another approach that people are thinking of using, because Skyrmions have smaller size, they're topologically protected, and you can apply a current to move them, and they can do various operations, like I showed logical operation and computational operations as well. So there are different approach. The field is moving, and we are hoping that we will be able to see some more applications in future.
Sure. Any iron piece is converted into a magnet when each domain of it becomes unidirectional. Is it possible for the human body to act as a magnet to attract others if each domain or atom becomes unidirectional?
Our body doesn't have iron, right? Like it is in hemoglobin, in the form of hemoglobin only.
Yeah.
So I am not very sure about that. But I know some bacteria which can create the iron particles into it. And those can also be arranged in a particular direction with the application of the magnetic field. So few bacteria do that, but I'm not sure about human body.
That was the last question, Professor. Thank you so much for such an insightful session. We will now proceed with a few formal announcements, so you are welcome to log out at this point if you wish.
Okay, thank you so much.
Thank you, Professor. Before we wrap up the session, we would really appreciate it if the audience could please take a minute to share your valuable feedback with us. The link to the feedback form is provided in the chat box. Please note that the recording of this session will be available on Ashoka's YouTube channel in case you would like to share it with your friends. The next episode of Scientifically Speaking Season 6 is scheduled for Tuesday, 24th September at 6 p.m. IST. The session will be delivered by Dr. Meghna Agarwala, faculty member of Department of Environmental Studies, Ashoka University. The title of the talk is Decoding Nature, from Prehistoric Sediments to Elephant Vocalizations. In this talk, Dr. Meghna will discuss how ancient lake sediments, dung, and elephant vocalizations can be used to study the relationship between plants, animals, humans, and their environment. This helps us to understand the balance between human activities and the environmental persistence to conservation. I would also like to inform our audience that registrations for the undergraduate program starting next year, that is August 2025, are now open. I would encourage students to register soon and have access to personalized mentorship with our academic counselors, interactions with Ashoka students to learn more about the campus life, and receive guidance from Ashoka's holistic admissions process. For more information, you can write to us at ugapply@ashoka.edu.in. This brings us to the end of this session. Please take care and stay safe.